By the end of this video, you will be able to answer the following essential questions. How are the vertical and horizontal motions of a projectile related? What is the relationship between projectile's height, time in the air, initial velocity, and horizontal distance? Marhaba! Welcome to Physics is Easy with Mr. Jesse. So you already have learned about the kinematic equations or the equations of motion that would allow you to describe the motion of an object that is moving horizontally like that of cars on the street, or an object moving vertically like that of falling objects. But what about when an object is moving both vertically and horizontally? Such kind of object could be considered as a projectile. A projectile is an object that is moving due to the influence of the force of gravity. So basically, any object that is being dropped or being thrown and is moving through air and acted upon by the force of gravity is considered a projectile. Consider a cannon that is lifted to a certain height from the ground. As the cannonball is fired, it will follow the path of the green ball, which is the combination of the projectile's horizontal and vertical motion. The path of a projectile is called a trajectory. As a matter of fact, as the cannonball is falling, it is also moving forward. Hence, we say that as the projectile moves, it can cover both horizontal and vertical displacement. This means then that projectile motion has two components: the horizontal component, which corresponds to the projectile moving forward, and the vertical component, which corresponds to the projectile falling. These two components are independent of each other. It is very important to note that each direction, either vertical or horizontal, is governed by different sets of equations. For instance, the horizontal component follows the rules of constant velocity, while the vertical component is describable using the equations that involve constant acceleration, because in this case, the object is experiencing a vertical acceleration equal to negative 9.8 meters per second square, or the acceleration due to gravity, since the only force acting on the projectile is the force of gravity. To demonstrate the independence of horizontal and vertical components of projectile motion, consider two marbles. One dropped from a particular height while the other rolls off a surface at the same height with some horizontal velocity. If these begin falling at the same time, they will strike the ground at the same instant because their vertical motion is independent of any horizontal motion. The one with horizontal velocity will cover some distance in the x direction, but it will fall downwards at the same rate as the one that falls straight down, and so they will have identical air times. So, if gravity is the only force acting on the projectile, why is it able to move forward when the force of gravity is only responsible for the projectile's fall or its vertical motion? The projectile, like this cannonball in the diagram, is able to move forward because of inertia. The explosion inside the cannon gives the cannonball its horizontal velocity, which we're going to call Vx, and thus it is able to move forward. Since there is no force that would cause the projectile to change its horizontal velocity, the acceleration in the horizontal component is said to be zero. Hence, the projectile covers a constant horizontal displacement, in this case, this delta x, that's delta x right there, delta x, and delta x for every time interval as depicted in this diagram. On the other hand, the vertical velocity of the projectile, which we're going to call Vy, is affected by the acceleration due to gravity. And as shown in the diagram, the vertical displacement changes in every time interval. So for instance, this is delta y1. This one right here is delta y2, which is much greater than delta y1. And delta y3 is much greater compared to delta y2. That's delta y4 right there, and delta y5. So these vertical displacements are not the same. And that is due to the fact that the projectile is accelerating in the y direction. Using PhET simulation, we can show the relationship between the projectile's time in air, horizontal velocity, and horizontal displacement. Here, our cannon is placed at a height of 15 meters and we will just change the initial horizontal velocity of our cannonball. Using this built-in tool, we can see the time in air, or the time it takes for the projectile to reach the ground, which corresponds to a height equal to 0, and the horizontal distance covered by the cannonball, or the range. We start with the initial horizontal velocity of 4 meters per second. That is its trajectory. Now we increase its initial speed to 8 meters per second, and let's see what happens. Now from 8, let's increase that to 12 meters per second, and let's see what happens. This time, let's increase that to 16 meters per second. And lastly, let's change the initial horizontal velocity to 20 meters per second. And now, once again, using this built-in tool, we will be able to see the time it takes for the projectile to reach the ground and the horizontal displacement, or the range. Let's check out these information for our first projectile, the one released with a horizontal velocity of 4 meters per second. So from the built-in tool, you can see that the time it takes for the object to reach the ground is 1.75 seconds and the range is 6.99 meters. For the cannonball fired with an initial velocity of 8 meters per second, the time it takes for the ball to reach the ground is still 1.75 seconds, but the range is now approximately 14 meters. When it was fired with 12 meters per second, the time it takes to reach the ground is still 1.75, but the range is about 21 meters. So when it was fired at 16 meters per second, still the time to reach the ground is the same, 1.75, but the range is approximately 28 meters. And lastly, when it was fired with 20 meters per second, the time it takes to reach the ground is still 1.75 meters, or rather seconds, and the range is approximately 35 meters. Now with this simulation, we can conclude that the horizontal velocity does not affect the projectile's time in air. However, increasing the horizontal velocity also increases the projectile's horizontal displacement. Still using this PhET simulation, let us investigate the relationship of the projectile's initial height of release, time in air, and its horizontal displacement or range. To do this, we will just change the height of the cannon from the ground while maintaining a certain initial horizontal velocity, which in this case is set to 15 meters per second. Let us start with a height of 4 meters and observe the projectile's trajectory. Now let's increase the initial height to 8 meters and let us observe what happens to the trajectory of the projectile. And then finally, let us set the initial height of release to 12 meters. Now let us utilize this built-in tool to determine the time it takes for the projectile to reach the ground, as well as its horizontal distance or range. Let us look at the projectile, or the trajectory of the projectile that was released at a height of 4 meters. As what you can see, the time it takes for the projectile to reach the ground when it was released at a height of 4 meters is 0.9 seconds and its range is 13.55. Now when the projectile was released at a height of 8 meters, the time it takes for the projectile to reach the ground is 1.28 seconds and it covers a horizontal displacement of 19.16 meters. And finally, when the projectile was released at a height of 12 meters, the time it takes for the projectile to reach the ground is 1.56 seconds and the range is 23.46 meters. With this, we can conclude that increasing the height from which a projectile is released results to an increase in the time in air as well as the horizontal displacement of the projectile. Now, for us to be able to solve problems related to projectile motion, let us revisit the equations of motion. The first one is applicable to the x component of the projectile motion since the velocity in the x-axis is constant. The delta x here is the horizontal displacement, while the t here is the time in air. On the other hand, these three equations are for the vertical component of the projectile motion, such that all of the v here would be the velocity on the x-axis. The acceleration here is going to be equal to g, and then this displacement in this equation refers to the vertical displacement, or delta y. Having all those considered, now we have our equations of motion for the projectile motion. This one right here would refer to the horizontal component, and these equations right here would be for the vertical component of the projectile motion. Consider this scenario. A cannonball is fired from a height of 10 meters with an initial velocity of 10 meters per second. Find the projectile's time in air and its horizontal displacement. To be able to solve this problem, we have to take note of the things that are given and the things that are implied. So things that are given are the following. Vx is equal to 10 meters per second. That's our initial horizontal velocity. We're also given the height from which the cannonball is being fired, and that is equal to 10 meters. And we are also aware, or we should also be aware, that the acceleration due to gravity here is equal to negative 9.8 meters per second square. And also, we know that the initial vertical velocity, or VIY, is equal to 0, because the object is just being fired horizontally. It's not being thrown downward or being thrown upward, so it does not have an initial horizontal velocity. Now we can solve for time. So solving for time, we will use the equation delta y is equal to VIYT plus 1/2 GT squared. This equation would allow us to solve for time. Let us substitute our values. Our delta y would be the final position minus the initial position. So the final position, the object is in the ground, that's going to be 0, minus the initial position, which is 10 meters above the ground. The initial vertical velocity is equal to 0, and time is what we need to solve for, plus 1/2. Acceleration due to gravity is negative 9.8 meters per second square, and again, time is what we need to solve for. So manipulating this problem, or manipulating this equation, it would allow us to solve for time, which would give us t is equal to 1.43 seconds. Now that we have the time of the projectile in air, we are going to use this to solve for the horizontal displacement, or the range, which pertains to the x component of the projectile's motion. So we are going to use the formula Vx, or the horizontal velocity, is equal to the horizontal displacement divided by the time in air. Then we substitute the values. Our initial horizontal velocity is given to be 10 meters per second. Then the initial displacement, or rather the horizontal displacement, is what we need to solve for, divided by the time that we were able to solve, which is 1.43 seconds. This would then give us a horizontal displacement equal to 14.3 meters. Let us use this simulation to verify our answers. Let's fire the cannon. The time it takes for the projectile to reach the ground is 1.43 seconds, and the range is approximately 14.3 meters. So I hope that you could now tell the relationship between the vertical and horizontal motions of a projectile, as well as the relationship of its height, time in air, initial velocity, and horizontal distance. For the next lesson, we will investigate the motion of a projectile that is launched at an angle. And that concludes this lesson. Always remember, physics is easy with Mr. Jesse.